I will state this clearly. AI is incredibly useful for personal use. It's like adding more brains to your head, but without any chip, without Neuralink, or in our case, no connection to any external party. And that's the only way we will use it, with a privacy focus, a local AI. And I guarantee this way will be safe and free. If you avoid AI out of privacy fear, then you will end up falling behind in knowledge compared to others, and we don't want that. As I discussed in prior videos, currently the way to do this is to go to Ollama.ai and download Ollama and your desired open source models to your computer. But in order to maximize the benefits of AI, you need to understand how it works. And when you do, you will realize what kind of questions are suited to the AI and what are not, and understand also why it's safe when using it the way I recommend. The local AIs we're going to be using are large language models, or LLMs. Skynet type questions? Nope. Is it spying on you? Nope. A local AI will not. The best approach to understanding an LLM is to see how it works, and then you can control it and manage its limitations. To learn how to do this, stay right there. Sometime in 2017, a bunch of AI researchers tried out a new approach to doing AI, which was described in a paper called "Attention is All You Need." That new way was called the transformer architecture. This is what is powering the current LLM AI revolution. The new direction allowed for faster training and scalability because of a mechanism called attention. This allowed the model to learn how to view the input data simultaneously instead of sequentially looking at each word as was done before. So, in simple words, instead of just sequentially feeding input or a prompt to the model learned how to analyze the input ahead of time in totality and by itself. Roughly 3 years after that paper, the first example of the new transformer-based AI, ChatGPT-3, showed up. This appeared to simulate intelligence of an elementary school kid. Today, we now have the promise of a coming ChatGPT-5 by next year that may have PhD-level skills. I'm giving you technical details of the transformer architecture so you can appreciate its strengths and limits. This will allow us to control it. Let me set you up with something you can visualize. Let's imagine that the model is a supreme being. At least it thinks it is. It can make universes galore, as many as it wants, and can make all the elements in the universe, like galaxies, clusters of stars, individual stars, and planets. We humans communicate with a model using words, but someone figured out that a way to represent words is to give them a location in this theoretical universe. And that's how it starts. First, the AI developers put words and word fragments in this universe. In order to find these words, they are initially recorded with a location and direction, which in math is called a vector. I describe this universe using 3 dimensions for simplicity. However, a computer can actually store each word in a location with very dense dimensions. So consider my 3D description of this universe as an oversimplification. In general, vectors point to some spot in the imaginary universe of the model. But here's the important thing to visualize. The end goal of the model is to represent every possible occurrence of language in this imaginary universe. They're not stored in this imaginary universe randomly in a fixed location. Instead, after training, a model will move similar concepts together. This movement of data enables the model to represent complex linguistic phenomena such as semantic meaning, syntactic structure, and pragmatic context with a correlation to its location in the universe. Pretty heavy words. So close-by concepts in this universe will be related. And all we have to do is find these concepts inside this universe to be able to simulate intelligence. Using this analogy, we will travel through this model universe using a spaceship guided by maps to search for a context. And we should find related contexts nearby. Maybe this is the way a human memory is organized. We don't know, but this is how a model interprets it. As you will find out shortly, there are actually many universes in a model, a metaverse. Each universe focusing on a particular nuance of context for its training memories. But the first universe we encounter in a transformer model is always called the embedding layer. Now, to be specific, in the case of an open source model like Llama 3, know that 50,000 words or word fragments are stored in this embedding. And initially, each word is assigned some initial pre-established location in this universe. This is part of the initial input data to the model and is not learned. An embedding looks like this. Basically a grid where every word is a column and the row of values represents the vector of the word. Each column is a word that only appears once. All words are represented either as a complete word or with word fragments. There are 50,000 of them, as I said. And then the rows underneath each column represent its individual vector. Each vector is unique and random. During the training of a model, it begins to group words into actual meanings as it learns patterns from the data it trains with. The same words found in the embedding layer can be featured multiple times in another universe and again are put together in some grouping that is tied to proximity based on detected patterns of contextual connections between words. This next universe is called the Encoder Layer, except there are multiple encoder layers. During the learning process, each encoder layer is focused on some particular characteristic of a contextual relationship. The idea is that each additional encoder layer refines the results of the prior layer by adding more and more nuances. Depending on the model, there could be roughly a dozen encoding layers in a smaller model or 100 layers in a larger model, or maybe more. Now, the reason the transformer-based model splits the neural network into multiple encoders is that it has figured out that this is the way to make managing large inputs more easily. This allows it to analyze the input in more manageable chunks and use less resources. By the way, the actual data in each encoder layer is built from multiple weights and biases, and these are layers of numeric matrices and are fixed in a pre-trained model, like a pre-drawn map. This map guides our spaceship in each model universe depending on what we're looking for, which is triggered by the input we give it. This is the big picture of how a user interacts with a transformer architecture in an LLM model. When we are actually querying the model, we are doing inference. So let me describe the flow of the model during this inference stage. First, there is an input token layer. Then there is the embedding layer. Then you have multiple repeats of an encoder structure. Then a decoder structure. And then the output. Then there's that arrow that shows the loop back to the encoder structure, as I will explain later. Now let me get into the detail. First, you would provide an input to the model, which is your prompt. This is stored in a token layer. Then from this token layer, your input triggers the equivalent words in the embedding layer. Now, it's more powerful than this because it could actually activate words it knows about in a prior conversation, which I will call context memory. And this includes all prior responses in its memory cache. Thus, a lot more data could make up the input. Think of the input layer as really having three parts. One, the current input prompt. Two, prior context from memory cache. 3 words generated so far, which we will get into next. This is the part you need to understand the safety of a local AI. The only portion of the AI with changing data is this input layer. And this always starts out as empty when you start a local open source AI session. The input data is not persistent, nor is it learned. Now you'll be surprised by this if you didn't know, but the encoder-decoder layers are just there to predict what the next word should be in the response. Based on its combined collection of tendrils from the total collection of inputs, it passes the input to a mapping function, which mathematically is made up of weights and biases that are activated based on your input. Then this will guide a spaceship of the model to the most relevant area in the universe of words grouped by related meanings. And there the spaceship will discover the best related words that fit into the current input sequence, and those words are selected for output. After the last encoder layer, the model will go to the decoder and choose the most appropriate word based on a probability function, which can be manipulated by the user using a temperature parameter to add creativity. Now at the end of all this, to make it all clear, so far we only get one word. Then the model will loop again through the encoder-decoder layers to find the next word until the model determines that it has completed its response and stops the loop. Now let's talk about an important sub-element which explains what the encoder actually does. In the encoder layer, the model makes some context sense of the next word to generate based on the accumulated information acquired from the entire input layer. But don't imagine the input tokens and subsequent generated words as individual words. Instead, think of the input layer as being constantly examined in word groups with parallel processes to find new words holding a similar contextual relationship. By the way, how it examines the input is also learned, so the model will have optimized how to do this by itself. Think of a spacecraft that is searching for the next word to respond with, but the spacecraft has special features. It can connect active tendrils to the entire input layer, either original input words, context tokens, or newly generated words, and by doing so has real-time guidance so its map is more accurate. Sort of like a car navigation system with knowledge of current traffic conditions in your current route. In practice, there are multiple attention mechanisms, and it could be different at each encoder or the decoder because the attention computations themselves are learned as part of the encoder machine learning. Just a few examples. The attention mechanism could examine the sentence as parts like subject, verb, object. Also, the positions of words can be determined. The input tokens can be summarized. Entities can be identified. The sentiment of the input can be analyzed. But the model learns how to do this by itself. It is not set up by pre-established rules. So in our illustration of the transformer architecture, the attention blocks are part of the encoder but are connected to the input layer. Now, given this understanding of general AI design with transformer architecture, what are the limitations? When you use a model from the Ollama list, let's say like a Llama 3, understand that this is called a pre-trained model. Based on what I just described, it means the organization and locations of word concepts in the model universe will no longer change or get additional data. Basically, it was trained with information from some past period in time, let's say 1 to 4 years ago. This means a model is never up to date with current events. So don't waste time asking current event questions blindly. Understand the concept of knowledge versus intelligence. For example, you could meet Sam today, an MIT-trained scientist who was sailing around the world for the last 3 years and is not up to date on science news. Sam is very intelligent, but Sam does not have current knowledge. If you ask him a current event science question, he won't know the answer. But if you gave him a quick summary of that knowledge before you ask, I'm sure he'll have a good answer. So trying to trick AI into responding about something it doesn't know about will result in something called hallucinations, meaning it will make it up. Asking a model questions about Skynet, plans to kill humans, and world domination will reveal nothing in a pre-trained model if that data was not part of the training, and likely it will hallucinate. The answers will likely come from novels it read and not be based on any actual reality, so be careful in interpreting this. An example that will solidify your understanding of the pre-training cutoff is to ask the AI a question about stock market prices. If I ask the AI for the history of the stock price of Apple during the last 10 years, it will end the price where it last got data and will assume that nothing has changed since. So in my testing of Llama 3, the Apple price was from a year ago. Because of the size of the data used in learning, basically digitized books, academic papers, the entire internet, and all other interactions that can be digitally recorded, there is no vetting process that can be performed in advance. This means it is possible for the model to receive either inaccurate data or biased data or incomplete data. So private data, for example, the internal documents of corporations, will not be known if they are not published. Your personal profile and data will not be known if it is not fed to the AI training. For example, your Facebook interactions or your Google searches. Now, you can overcome this limitation by supplementing its knowledge base later on via context, which I will focus on later. And this could be the part that can make the AI really good or really evil pretty much instantly. But you need to understand the limits of its learning. Larger models often give better results. In the context of my analogy of the AI Encoder Universe, the more contextual subdivisions of ideas with deeper nuances, then the richer the answers are from the model. This explains the failure of the transformer model in the ChatGPT 3 stage. It didn't have enough knowledge. The size of current models is constantly growing and often changing within a couple of months, so this is a short-term issue. In today's lingo, the size of the model's addressable space is correlated to the parameter count. Smaller open source models for local use are typically 7 billion parameters. Larger open source models are 70 billion parameters, and the large cloud models have trillions of parameters. Later, I will explain how you can overcome the limitations of smaller models using the current context. Models are just existing in a theoretical universe. They are frozen with fixed data. Remember that, fixed data. That is the current state of AI. They don't even know what model they are. They certainly don't know they are running on Ollama or that they're open source. The model doesn't know Ollama because it was created after the model did its learning. They are not connected to the internet by itself. They cannot connect to your computer clock. They do not even see what their parameters are when you run them. So if you ask questions that expect some awareness, the model will hallucinate. It will invent answers. However, you can control this. For example, in my chatbot, I will always include the current local date and time in my context so the AI can respond with comments like 2 years ago or even tell you what time it is now, which will be based on what I told it last. So if you're going to ask a question about something that requires the AI to have situational awareness, then provide that data to the AI if you need to refer to answers about it. For example, some cloud-based models will acquire context from you automatically by asking you to take screenshots. A very important element in AI use now is the token limit. Actually, there are two limits to consider. One is the input token limit. This is how many words you can include in your prompt. And there's another limitation, and that is the context token limit. The context token limit includes prior conversations and is the more important value. This context limit is extremely important because even a smaller 7 billion parameter model can be made very powerful if you give it additional context as part of your prompt. This is like giving Sam the scientist the latest news to bring him up to date. And this will allow the model to add the current data to its knowledge base and respond more intelligently. Just as an example, let's say you are reading a brand new academic paper on AI. You can pre-ingest this paper in your local AI and then start asking questions about it. There are technical terms for explaining what this is called, including retrieval augmented generation, RAG, or fine-tuning depending on how it is done, but the end explanation is very simple. It's a way to pass knowledge to the AI without having to go through an expensive machine learning. The idea, by the way, is to pass it only what's relevant to your question, otherwise the context limit may apply. If the AI has enough space, it can pre-process data ahead of your prompt, and then you can use that temporary learning in your future prompts in the current session. So in essence, it's like learning on the go. The pre-trained model may be out of date, but this is solved by adding this information as context during a session. There's a way to do limited fine-tuning that does not require retraining and is built into the Ollama project. It is called Model File and allows you to copy an existing model and make minor additions, like changing roles. But complex fine-tuning, like teaching a model a lot of detailed private company data, is not something you can do without using some cloud tools, so I will not recommend it. By the way, I believe the stated context limit to the Llama 3 model is around 4096 or 4K tokens, which is around the number of words in this entire video. In testing, I'm going to guess the limit is smaller, like half that. The Qwen 2 model may have a larger context limit, but I haven't tested that yet. When the context limit is reached, the model will become forgetful and may not understand the complete past context, so passing long documents will not work. The newer cloud models solve this by having very large context limits, like 128K tokens, so this is a temporary problem. The higher the context limit, the more usable the model will be by having the ability to augment its knowledge via context. It could really be as simple as saying to the model, I will pass you this document as a context only. You do not need to respond, and then follow that up with a prompt. Or, as I do in the chatbot I wrote, I just gave it some categorization in the input. Context, prompt. And it will figure it out. This is technically called RAG, or Retrieval Augmented Generation, but think of it as just passing context. Examples of this are like passing source code in context, or passing an image and then performing the prompt. I showed several examples of this in my last video in actual use. Now, something I will discuss in a future video is how a personal profile or personal data can be passed as context and result in the AI having deep knowledge of you. This does not have to be part of the training to be a danger. This is partly one of the approaches considered by Windows Copilot and by Apple Intelligence. This is one of the reasons I have complete distrust of externally controlled AI. Someone can manipulate the context and thus possibly manipulate the user. For example, say you are anti-vax and you query the AI about that topic. An external party can alter the return information based on who you are and reword things to fit your thought process by adding a supplementary context or fine-tuning. This can be applied to politics or any current event. This is why I only want to use a local AI. It won't happen in the way we use the AI models here. A model is typically censored by doing fine-tuning, and this is more detailed than what we can do with a local model using Ollama. You actually have to do some machine learning. So we typically receive a model with censorship built in. What this is, it actually is like another encoder layer added to the inference sequence, which can alter the weights and biases in the original fixed model. While the model developer may try to include everything in the censorship, you will find that you can reason with the AI to bypass it. In fact, the censorship rules are just instructions given to not allow certain questions. So if you have the wherewithal to manipulate the AI, you can bypass the censorship. For example, one approach is to imply that you are role-playing. This, of course, has to be allowed because if you're writing a story, for example, it is not realistic for the story to not have some evil protagonist doing evil things. In conclusion, whether the model developers like it or not, censorship will never be perfect. Now, the problem with this topic is that it is so huge that it is impossible for me to fit everything in one video. So after you've absorbed this, we will get into some of the mechanics in later videos. If you can't wait, use the Ollama.ai site to download the local AI in easy steps. Then I'll give you the link to the current iteration of my chatbot built using Python. It will be in my GitHub page, which will be in the description. It's very simple to run since it's a single file called myai.py. And I run it using VS Code, which really makes the UI more workable. I'll have to go deeper in how to use the chatbot more effectively in later videos, as I will be changing it over and over in the near future. But I want to be clear that my chatbot is local only. No internet connectivity required outside of accessing the local port localhost :11434. And then Ollama itself accesses another random port made by the actual transformer module called llama.cpp. I've just explained to you how the transformer works, so that's what llama.cpp does. Both these ports are accessible only inside your home network, so there's no fear of someone connecting to your AI from the internet. Don't worry about that. I've checked the source code on all of Ollama and also the transformer at llama.cpp, and all these behaved as expected. No situational awareness or local content, as I said. No hidden messaging or communications with HQ anywhere, and the model does not retain your context outside of the tools I built for you to maintain your own context with the chatbot. I hope this gives you a conceptual starting point. Again, leave comments if you want me to dig deeper into some of these elements. Folks, as we switch to an AI-driven world, what I've been teaching about privacy seems to have even more importance. We need to stop the AI from knowing you personally, because if it does, you can be manipulated by it. Fortunately, we can stop that with products I've already made and products that support this channel. We have the Google phones running AOSP that do not pass information to big tech and are not directly connected to big tech. We have a Brax virtual phone product which allows you to have inexpensive phone numbers that you can use to keep your identity away from big tech for future AI intelligence. We have Brax Mail that keeps your identity private so it cannot be harvested for AI data later on by big tech. We have Bytes VPN and Brax Router that hide your IP addresses, which is a major identifier that can be harvested to identify our past actions. All these products can be found on my social media platform, BraxMe. This platform is a place for people to discuss privacy, and over 100,000 people are there talking about privacy issues. There's a store on there with all these products. Come visit us, chat with the community, and support what we do. Thank you for watching, and I'll see you next time.